Hello there, in this video we're going to be solving an example optimization problem. So a rectangle is inscribed in an equilateral triangle so that two of its vertices are on one of the sides of the triangle, while the other two are on the other two sides of the triangle. Suppose the side of the triangle is 4. Now the question asks, find the maximal area of the inscribed rectangle. So I'm just going to go straight ahead and show you what the diagram should look like. It's going to be an equilateral triangle. All sides are going to be the same, and it's going to have a rectangle inside, and it's going to look like this. So the first thing I'm going to be doing here then is labeling the triangle with everything we're going to be needing. So I'm first off going to divide this in half so I can just work with one of the sides. Then I'm going to start labeling everything. So let's label this down here, this vertex right there. Let's label that an A. This will be a B, and let's keep moving forward throughout everything. This will be D. That top one up there is an E, and this will be an F. And let's say the thing right here, the actual line inside for the rectangle, that's going to be X. And this one right here, because it's going to be, it should be a Y. But since we're dividing everything by 2, it's going to be Y divided by 2. And we're going to be using the property of similar triangles to find a relationship amongst this larger triangle here and the smaller one right here. And the reason I'm doing this is because I want to associate X and Y with, in this particular question, the area of a rectangle. So mind you, the area of a rectangle is equal to the width, or X, multiply the height, or Y. So first off, the similar triangle states that if the line AE right here, if I divided that by the line AC down there, I would get the same value that if I were to divide the line BD by the line BC. So we have the line AE divided by the line AC down there. So the line AC should be equal to then the line BD divided by the line BC, the one down there. So BC. So now let's start figure out finding the values of each of these lines. So what is the value of line AE? Well, for that one we can use the Pythagorean theorem. And if we rearrange the Pythagorean theorem to figure out what this particular line would be, it essentially we would get something like, let's say A was equal to square root of essentially C squared subtract B squared. That's essentially what it would be. So what is the value of C? Well, in this particular case, we're saying C is this hypotenuse, and it's an equilateral triangle, and it mentions in the question that it has a side of 4. So we know that C has a value of 4. So it's going to be 4 squared subtract B. So B then is this line down here. And because it's an equilateral triangle and we're dividing it in half, 4 divided by 2 is going to give you a 2. So this value down here is going to be a 2 squared. And we're going to be square rooting it all to get the value of this line right there. So if we did that, this would be a 16, this would be a 4, that would give me a 12. And if I square root the 12, well, it's just going to be square root 12. So that the square root 12 then is going to be the value of the line AE, this middle one right there, the height of the triangle. So let me erase some of this. And we now know that. So square root 12 is the value of the line AE, and it's being divided by the line AC, the line down here. Well, we already know that value is a 2, right? So let's put a 2 down there. And that's going to be equal to the line BD. The line BD is the one right here. So it's kind of hard to find the value for that, but notice that it's equivalent to X, and X is one of the sides of the rectangle. And this is the part where we start associating the diagram with the sort of equation we created using the similar triangles law or rule. So we're saying the line BD then is equal to X, and what is the value of BC? Well, BC is also a bit tricky to figure out. You need to notice that BC, this line right there, is going to be equal to, if we took this larger line, and we subtracted it by this smaller line right over here to the left. So then, what is the value of the line AC? Well, we know that's 2, so if we divide, it would be 2 subtract, well, this line right here. What is AB? Well, the line AB is equivalent to this right here, y divided by 2. So let's just put that in, y divided by 2. And now we effectively substitute all of the lines with some kind of value. We formed an association with the x and y's for this formula right there. So now the next step I'm going to be taking is isolating y, the value of y. And, well, why am I going to be doing that? No pun intended. I'm doing that because I want to substitute whatever that is into this formula right there. And the entire goal is to get the area formula under one variable. So let's start solving this for y. Let me erase this because it's no longer necessary. Well, if I multiply both sides by this term right there, I would get something like this. 2 subtract y divided by 2, multiply square root 12 over 2. That would give me equal to x. And if I threw, I would get, well, notice that this 2 here and this 2 here would cancel out if I multiplied this term to there. So that would just give me a square root 12 on that side, subtract, and it's going to be multiplying by there. So that would give me a square root 12, square root 12y, then divided by 4. So all of that divided by 4. And this will be equal to x. But I mentioned that we want to isolate y, not x. I mean, you could just do x, but I want to do y because y is always, it's fantastic. Anyways, well, we can rearrange the equation. We can do square root 12 subtract x is going to equal square root 12 divided by 4y. And if we divided everything by this value right there, we would isolate a y essentially. So let's do that. Square root 12 divided by 4. And now that we've isolated y, which was the goal, let's simplify it a tad bit more because that's a lot to work with, especially for later on. So how can we simplify this? Well, we can notice that if we divided them separately like that, well, square root 12 divided by square root 12 divided by 4 is going to give you a 4. So we'd have 4 subtract, and what's this one? Well, that'll give me a 4x divided by square root 12. So this is all going to equal y. So this is what we have now, and that's as simplified as we can make it. Well, that's as simplified as we can make it where it would actually be useful to simplify it. So now that we know what y is, let me change colors. This is getting a bit boring. There we go. So let's substitute this y value right here into the area formula and actually start making some better progress, I guess. So it's going to be x on the outside, multiply 4 subtract 4x divided by square root 12. And that's going to equal the area in this case, actually. So it's going to give us the area. So what is this? And that'll give me 4x if we actually multiplied it through. So 4x subtract, that'll give me 4x squared divided by square root 12. And let me erase that down there. We don't really need that. Sorry if I'm going a bit fast. I can only record for so long before I run out of memory. Now all this is equal to the area. And now the next step is just to take the derivative of this of the area because, well, that's generally what we do in optimization problems. So the area is going to be equal to, well, what's the derivative of 4x? Well, that's just a 4. Subtract the derivative of this, which would be, if we took the 2 down there, it's going to be 2 multiply 4x divided by square root 12. And now that we know that, the next step is to isolate, because this is essentially the derivative of the area formula. The next step, as I was going to say, is to find the critical values or the critical points. So let's go ahead and do that. The only way we can do that in this particular case is to solve x for 0. Essentially, we just have to isolate x. So let's go ahead and start doing that. Now, if I were to put this over there, I would get negative 4 is equal to negative 2, or I should say negative 8x over square root 12. If I divided everything by square root 12, however, let me erase this down here. Hopefully I didn't make any mistakes so far. If I actually divided everything by this term right there, I would get negative 4 divided by negative 8 divided by square root 12 is going to be equal to x. And because they're both negative, we can just cancel that out. If you put a 12 up there and an 8 at the bottom, they can cancel out because you would have a 4 on top. Well, essentially, it's going to look like this. X is going to equal, and it's going to equal square root 12 multiply 4 divided by 8, which is going to give me a half. So it's just going to be literally square root 12 divided by 2. And that's going to be what x is equal to. And yeah, I am going really fast at this, and I do apologize. I do wish I can go slower, but time is quite the constraint. Now this, essentially, if you do the algebra, it's going to equal square root 12 divided by 2. And that's going to be the x value. It's going to be a critical point, a critical value. And it's one of many. Because notice this value right here, it could be the minimum x value you can have or the maximum. We're trying to look for the maximum. We don't know what this one is. So we need to test it against what x could possibly be. Its upper limits and its lower limits. And, well, what do I mean by this? Well, what is its lower limits? How small can x possibly be in this question? Well, x can't be a negative. I mean, you can't have a negative side, right? So the interval then is going to be from 0 to, well, what's the highest value x can ever be? Well, you can't have an x value that's greater than a triangle itself. And we know that the height of the triangle is square root 12, right? That's this middle line right there. So x can't be greater than that. So its upper limit then is square root 12. And essentially, either of these values, this 0 here, this square root 12, or this critical value that we found, they're all critical values in their own right. Any of these could be the maximum we're looking for, so we need to test them. So how do we test them? Well, we would actually put them against the derivative for the area we found, which I totally erased, which is kind of funny because I need it. So let me just see if I can back up. So the area formula we found was 4x subtract 4, x squared divided by square root 12. So what would happen then if we put so remember the limits are 0 up to square root 12, and the x value we found was, I believe, square root 12 divided by 2. So what happens if we put a 0 inside this formula as a possible x value? What kind of area would you get? Well, you would actually get an area of 0. So that's not too helpful, but so let me just make a little column here. So put a 0 in there, you're going to get a 0 out as the area. What happens if you put a square root 12 inside? Well, if you did that, notice that if you put a square root 12 in this one, it's going to cancel out with the bottom. So that means this term right here is just going to be 4 multiplied square root 12. But if you put the square root 12 in this one, it's also going to be the same thing. So if you subtract it, it's going to give you a 0. So if you put a square root 12 in this area formula we made, it's going to give you a 0 as well. So we know those can't be it because we're looking for a maximum, not a minimum. These two, I guess, would qualify for a minimum. And it does make sense. I mean, what is the smallest rectangle you can make in a triangle? Well, its area is going to be 0. So notice that in the question it asks, find the maximal area of the inscribed rectangle. So what is the max area we can have? Well, assuming if we put an x value of this inside, and that gives us the maximum area, let's just put that inside and see what we get. Now, if you substituted the x value of square root 12 over 2 into this formula, you would get a value of square root 12 as the final area for this problem. This is the maximum area this rectangle in here can take in a triangle, an equilateral triangle that has a side of 4.